Jurahimon Kimura was a supercentenarian who lived until he was 116 years old. Now, in an earlier video, we looked at Jurahimon's blood test data for the last 4 years of his life, and we identified which biomarkers were good and which biomarkers were not good. Now, that was part one, and note that there's more blood test data that was published in that paper, so let's have a look. So correspondingly, this will be part two of Jurahimon Kimura's blood test analysis from when he was 112 through 116 years old. So which biomarkers will they cover? Well, they include the 10 biomarkers here: uric acid, total protein, 4 markers of liver function, hemoglobin, hematocrit, platelets, and total cholesterol. So starting with 3 data points, so when Jurahimon was 111.5 years old, 113.3 years old, and 115.7 years old, we'll identify what was good or what appears to be good and what was bad. So unfortunately in this video, most of it is going to be biomarker data that was going in the wrong direction rather than right. So starting from the top, uric acid. Let's put this Jurahimon's data into context. So here we're looking at the hazard ratio for all-cause mortality plotted on the y-axis against the concentration of uric acid. And we can see that lowest all-cause mortality risk is when uric acid is 303 micromolar or 5.09 milligrams per deciliter. So when taking Jurahimon's average value over 3 blood tests, his average uric acid was 263.5 micromolar or 4.43 milligrams per deciliter, and we can see that his data is not far from the lowest all-cause mortality risk for the association with uric acid. So from this, we can conclude that his uric acid data is close to optimal. Now, as an interesting aside, note that uric acid accumulates when kidney function is impaired or suboptimal. And in part one, we saw that Jurahimon had suboptimal kidney function as indicated by elevated cystatin C and blood urea nitrogen bun. So an important question to ask would be, why isn't uric acid correspondingly increased when considering that he may have had suboptimal kidney function? So one possibility is that he may have had a relatively low intake of dietary precursors that can be degraded to form uric acid. But note that there are no published studies that exist for his usual dietary intake to verify that hypothesis. All right, moving along, total protein. So total protein levels decline during aging for both men and women, the data for men in green and the data for women in blue. And note that I'm only going to go over the data for men as it directly applies to Jurahimon. So 20-year-olds have total protein levels in blood of about 7.4 grams per deciliter, and then they decline during aging such that 90-year-olds or older have total protein levels less than 6.6. So when we look at Jurahimon's average total protein levels, we can see that he's somewhere in the middle, somewhere close to around 60 years old, based on his average total protein of 7.07 grams per deciliter. Now, superficially, that seems pretty good because he was 116 or in the 112 to 116 range over these 3 blood tests. So he's at least 50 years younger based on his total protein levels. But note that total protein equals albumin plus globulin. And in part one, we saw that Jurahimon had aged and unhealthy levels of albumin. Now, when we subtract albumin from total protein, that equals globulin, which is also known as the gamma gap. So we can do that here and calculate Jurahimon's globulin or his gamma gap and get the values there of 3.2, 4.0, and 4 grams per deciliter. So let's put that data into context. So here we're looking at survival probability or all-cause mortality risk plotted on the y-axis against time after the baseline assessment of globulin or the gamma gap. So it was about a 5-year follow-up after the baseline assessment of globulin levels. So note that this study was in people who had an average age of 94 years, which is relatively close to Jurahimon's age, 20 or so years. But I'd expect that this data would be more relevant when comparing a study in 50-year-olds. So what does the data show? So for people that had a gamma gap, again, those are globulin levels, less than 3.2 in blue or greater than 3.2 in red. Starting with the people who had relatively low globulin levels, we can see that they had an average life expectancy, a median survival when looking at 50% survival, which is what the green line indicates, of about 44 months from the baseline assessment. However, people that had higher globulin levels or a higher gamma gap lived significantly shorter, as shown there. And note that Jurahimon's average globulin level or his gamma gap was 3.73 grams per deciliter, which would put him on that red line for a significantly shorter life expectancy after the baseline assessment when compared with people who had a lower gamma gap. So relatively high globulin, as evidenced by the gamma gap, and low albumin reflect the bad for health phenotype. So although total protein may have looked 50 years younger superficially, when we investigate deeper, when we investigate further, we see that his albumin and globulin levels were not optimal, in fact, far from optimal. So moving along, we're going to look at four markers of liver function: GOT, GPT, gamma GTP, and cholinesterase. So starting with GOT, GOT stands for glutamate oxaloacetate transferase, and that's also commonly known as aspartate aminotransferase, AST. So let's put his data into context. So here is all-cause mortality data for GOT or AST, and we've got it in 4 quartiles with lowest risk for people who had AST or GOT in the 21 to 23 range when compared with the referent, which was a median value of 20. So Jarahiman's data was 29 for average data for GOT, and based on that, that would put him in quartile 4, which had a median value of 27, which would indicate he had a significantly all-cause mortality risk based on his GOT data. So his GOT data is not good, as it would be associated with an increased all-cause mortality risk. All right, what about GPT? So GPT stands for glutamate pyruvate transferase, and this is also more commonly known as alanine aminotransferase, ALT. So let's put that data into context, looking at all-cause mortality data for ALT or GPT. So Jarahiman's average GPT was 14.7, and when compared with the reference, or actually that would put him into the reference group that had a median value of 15. Now normally the reference, or I shouldn't say normally, but most often, the reference has the lowest risk for all-cause mortality, but that's not the situation in this case. As we can see, Q2 and Q3, with median values of ALT of 18 to 22, had a significantly reduced all-cause mortality risk when compared with people who had ALT values of 15. So that would indicate that Jarahiman had significantly increased all-cause mortality risk based on his GPT levels. Now, so note that his GPT would also not be good or a little bit far from optimal. Now, besides assessing all-cause mortality risk for GOT and GPT individually, evaluating their ratio, or GOT divided by GPT or AST divided by ALT, has value. And that's what we can see here with average AST or ALT over ALT values of 1.9, 1.9, and 2.1 at those 3 different data points over that 4-year period. So let's put these data into perspective. So here we're looking at survival rate on the y-axis, or all-cause mortality risk, for people who had a relatively low AST-ALT ratio, in which case their ratio was 1.02, their average ratio. And that was compared against the survival rate for people who had a relatively high AST to ALT ratio, as shown there in red. And their average AST to ALT ratio was 1.83. So these 2 curves are significantly different. In other words, people who had a relatively lower AST to ALT ratio had a lower risk for all-cause mortality when compared with the group that had a higher AST to ALT ratio. So note that Jarahiman's average AST to ALT ratio is 2.0, which would put him pretty close to the high AST to ALT ratio group, which also would put him at a significantly increased all-cause mortality risk based on his ratio. So that data too is not good. All right, so moving along, gamma GTP, which is known as gamma glutamyl transpeptidase, and that's also more commonly known as gamma glutamyl transferase, or GGT. So let's put that data into context by looking at all-cause mortality data, which is shown there. And in this case, lower is better in terms of all-cause mortality risk, with a median value of 12 in Q1 being associated with lowest all-cause mortality risk, and then risk significantly increases as GGT increases from the median value of 12. So Jarahiman's average gamma GTP ratio was 41, which would put him somewhere in between Q3 and Q4, which had median values of 32 and 58. Nonetheless, both are associated with an increased all-cause mortality risk, so Jarahiman's gamma GTP data is also not good, unfortunately. All right, and then last for these 4 liver markers is cholinesterase. Now, in contrast with these other markers that I've just presented, which are commonly performed when one goes to their doctor for their annual physical on a blood test, cholinesterase is not. So let's dig a little deeper into what cholinesterase is. So obviously, it's a liver enzyme. As I mentioned, these are 4 liver enzymes. And within the liver, there are different liver cell types, one of them being hepatocytes, which is zoomed in that circle. So cholinesterase is an enzyme that's produced within hepatocytes. And when liver function is reduced, less cholinesterase is made and then released into the blood. So note that cholinesterase declines during aging, which is shown here from the age range of about 50 to more than 110 years old. So when looking at Jarahimon's, well, and you can see the clear age-related decline with that red arrow. So when looking at Jarahimon's average cholinesterase data of about 199 international units per liter, that would put him at, by extrapolation, somewhere close to the 110-year-old data point, which is pretty close to his actual chronological age. So from this, we conclude that Jarahimon had aged and not youthful levels of cholinesterase. So what about all-cause mortality risk? And that's what's shown here in data from the same study. And note that all of these studies, if you're interested in checking out the papers, they'll be linked in the description box for the video. So here we can see that having a relatively higher level of cholinesterase is significantly associated with a reduced all-cause mortality risk. As you can see, the confidence interval, the data in parentheses, is completely below 1, which indicates lower all-cause mortality risk with a higher level of cholinesterase. However, Jarahimon has relatively low levels of cholinesterase, so this would put him at an increased all-cause mortality risk. So based on that, we can see that collectively these 4 markers of liver function, Jarahimon's liver health/function and/or function was suboptimal and potentially poor. All right, so moving along, hemoglobin, we can see his 3 data there, 11.6, 12.8, and 12.0. And let's put his data into context. So here we're looking at all-cause mortality in men. And note that for each of these data that I present in the video, I go after the largest studies that are representative of the majority of studies as I do deep dives. I don't just look at one paper, I look at as many papers that exist for a given biomarker as possible, and then present the data for the largest study that exists on that given biomarker. Now, in case I missed a study, feel free to leave it in the comments, and I'd be glad to give you a shout out and present that data in a future video. So here for hemoglobin, when compared, actually Jarahimon's average hemoglobin level is 12.1 grams per deciliter. So when compared with the reference, which was 14 to 14.9, we can see that Jarahimon is at a significantly increased all-cause mortality risk based on his hemoglobin level. So that would indicate that his hemoglobin levels, unfortunately, are not good. All right, what about hematocrit? So hematocrit is the percentage of red blood cells, RBCs, that are present in blood. And in part 1 of this video series, we saw that Jarahimon had aged and not youthful levels of red blood cells, so it shouldn't be a surprise that his hematocrit is also relatively low. Nonetheless, let's put his hematocrit data into perspective by looking at all-cause mortality data, which is shown here. So all-cause mortality risk on the y-axis, plotted against the percentage of hematocrit on the x-axis. So as we can see, lowest all-cause mortality risk is when hematocrit is 43.5%, and Jarahimon's data is 37.7, which, although it isn't too far, it's definitely going in the wrong direction. So from that, we can conclude that his hematocrit was suboptimal. Note that if his hematocrit was somewhere around 30, it would be even worse. But nonetheless, it isn't great. It's not as good as uric acid, which is relatively closer to the lowest risk for all-cause mortality when compared with hematocrit. All right, next up are platelets. So note that platelets decline during aging. Again, this is data in men. It's a study of more than 230,000 men. So starting from the age range of 20 to 30 years all the way through 90 to 100 years, we can see that platelets, which start off in about the 230 range up until about 50 to 60, they then decline after that with values approaching less than 210, so approaching 200 as you approach about 100 years old. So note that this is up to 100 years old, so it isn't a far stretch to expect that platelets would further continue to decline, which would be one potential explanation for Jarahimon's average platelets. Sorry, that's a mistake there. It should be Jarahimon's average platelets at 173.7 thousand platelets per microliter. Now, note that the units for the data for platelets are 18.8, 16, and 17.3. So if we multiply that data by 100, we get 188 times 10 to the 3 platelets per microliter, in case you were wondering why the data looks different in terms of the units. All right, so let's put his platelet data into perspective for all-cause mortality risk, which is shown there. So in this study of more than 131,000 people, when compared with people who had platelets in the 200 to 300 range, which was defined as the reference, we can see that people who had platelets in the 100 to 200 range, which Jarahimon does, they had a significantly all-cause mortality risk in the multivariate adjusted model and in the crude unadjusted model, as shown but by the 25% increased all-cause mortality risk there too. So nonetheless, increased all-cause mortality risk for platelets based on Jurahimon's platelet data. So for that, we can conclude that his platelets, they were aged, not youthful, and unhealthy based on the all-cause mortality data. All right, next up, and last but not least, total cholesterol. So in part one, we saw that Jurahimon's HDL and VLDL, which can be calculated simply by dividing, or a very close approximation by dividing triglycerides by 5, HDL and VLDL were among the what's good list for biomarkers in part one. Now note that total cholesterol equals HDL plus VLDL plus LDL, so this could potentially be a mostly LDL story, and I'll have more on that coming up in a bit. So let's look at let's look at the all-cause mortality data first, and then look at the aging data second. So here we're looking at all-cause mortality data for total cholesterol, and this is in people who are 75 to 99 years. Again, I was trying to look at representative data for an age group that was as close to Jurahimon's age group as possible. So when looking at Jurahimon's average total cholesterol of 153 milligrams per deciliter, as indicated there, we can see that that's significantly associated with a significantly increased all-cause mortality risk when compared with relatively higher total cholesterol, which in this case was lowest risk of for people who had total cholesterol in the 200 to 229 milligram per deciliter range. So from that, we can conclude that Jurahimon had a significantly increased all-cause mortality risk based on his total cholesterol data. So let's have a look at the aging data. How does total cholesterol change during aging? And that's what's shown here, all the way up through 88-year-olds, and this is in a study of more than 12.8 million people. So total cholesterol increases during aging for both men in green and women in red, as shown there, up until about 50 years. So it goes from about 160 to 200, up until 50 in men, and then after the age 50, it declines all the way to about 180. Now, note that Jurahimon's total cholesterol had an average of 153, so it may not be a far stretch to think that his total cholesterol levels may have been higher in youth and then continue to decline after 88 in this data here to his 153 for the last 4 years of his life. So that's what's stated there. Was Jurahimon's total cholesterol relatively high, but then declined until reaching 116 years? So that's one possibility. Alternatively, also note that relatively lower total cholesterol, somewhere around 160 in men, for people who were younger than 20, around 18 years old, lower total cholesterol is also found in youth. So another question that we can ask is Jurahimon's total cholesterol of 153, that average value over 3 years, indicative of youth? So we can assess that by looking at data for albumin and HDL. And that's what's shown here. Albumin and HDL can be used to further evaluate all-cause mortality risk when total cholesterol is less than 160 milligrams per deciliter. So first, starting off, and note that all 4 of these data are in people who have total cholesterol lower than 160. So starting within that group, and granted, this is a very small group. It's only 393 subjects. There isn't a lot of published data on this subject, at least in terms of all-cause mortality risk, total cholesterol lower than 160, and then other biomarkers in assessing whether that low total cholesterol may be neutral, beneficial, or detrimental for health. So in this relatively small study, and again, if anybody's come across a bigger study that tried to stratify all-cause mortality risk in people who had lower total cholesterol, please post it in the comments. Please share that data. So starting with people who had a total cholesterol less than 160, relatively low albumin of 38 grams per deciliter, and relatively low HDL of 47 milligrams per deciliter, that was defined as the reference starting on the left. And then for people who had high HDL, but also relatively low albumin and low total cholesterol, all-cause mortality risk was similar to people who also had low HDL. So HDL didn't impact all-cause mortality risk for people who had relatively low total cholesterol, less than 160. But what happens when those people had relatively higher albumin? And now we can see a significantly reduced all-cause mortality risk for people who have low total cholesterol, less than 160, relatively high albumin of greater than 38 grams per deciliter, but then also relatively low HDL. So in this case, it's a 32% reduced all-cause mortality risk when compared with someone who has a low total cholesterol, low albumin, and low HDL. But even better are people that have low total cholesterol, relatively high albumin, and relatively high HDL, higher than 47, as shown there. There's a 62% reduced all-cause mortality risk when compared with people who have low total cholesterol, low albumin, and low HDL. Now, these data can be more easily simplified by looking at a flowchart here. So starting with low total cholesterol at the top, and in Jarahiman's case, he did have low total cholesterol with an average of 153 milligrams per deciliter. And then taking it from there, did he have low albumin or high albumin, relatively high albumin? In his case, he had relatively low albumin with an average data of 3.3 grams per deciliter. That should be deciliter. Sorry, that's correct. Those units are correct. 3.3 grams per liter for albumin. So that would put him at highest risk for all-cause mortality based on his albumin and total cholesterol data. Note that if he had high albumin, and then correspondingly either low or high HDL, we could then look at intermediate risk and low risk, but that's not the case in Jarahiman's data. So in his case, his relatively low total cholesterol in combination with low albumin but high HDL may not be indicative of youth, but an increased all-cause mortality risk. So as a summary for part 2, we identified what may have been good, uric acid, but then there was a lot going in the wrong direction in terms of Jarahiman's blood biomarkers. Now, when considering in part 1, as I showed that his glucose, HbA1c, HDL, triglycerides, white blood cells, and CRP were in the CRP at least for the first data point when he was 111.5 years old, were in the what's good category, it highlights a potentially important role for these biomarkers on longevity, especially when considering that he had a multitude of not good biomarkers of kidney, liver, red blood cells, and red blood cell related measures, including hemoglobin and hematocrit, platelets, and total cholesterol. Now, if you read the paper, you'll notice that only one biomarker is missing from the 22 that were published, and that's LDL. And that's because in a very recently published paper, which is shown here, they stratified cardiovascular disease risk based on LDL levels and glucose levels, which may contribute to identifying when relatively low LDL, in Jarahiman's case, would be associated with an increased cardiovascular disease risk or mortality from cardiovascular disease or not. So I'm probably going to make a future video about that, so stay tuned for that. All right, that's all for now. If you're interested in more about my attempts to biohack aging, check us out on Patreon. Thanks for watching. I hope that you enjoyed the video. Have a great day.